It feels like, we are just drowning in information these days.
Yeah.
Trying to make sense of it all can be so overwhelming.
Yeah.
But what if there was a way to connect all those scattered data points to really see the underlying connections?
Well, that's the promise of knowledge graphs, or KGs.
Okay.
You can think of them as intelligent networks where things are connected by relationships.
Okay.
Entities are connected by relationships.
Yeah.
And we're seeing their impact just growing so rapidly.
Yeah.
We're seeing them in critical areas like understanding the spread of COVID-19,
Right.
managing the insane complexity of railway operations, even streamlining IT incident resolution.
Yeah, absolutely. And our sources highlighted those exact applications.
Yeah.
COVID Research 17, Railway Networks 16, and IT Incident Management 22.
Right.
It's clear that KGs offer such a powerful way to organize all of this knowledge.
Yeah.
But here's where things get really interesting. While KGs and the languages that we use to build them, declarative mapping languages like RML and R2RML, are becoming more popular,
Right.
a lot of them lack a solid formal foundation.
Right. And that lack of formality can create some pretty significant challenges.
Okay.
Without precise underlying rules, different software tools interpreting the same language can produce different results.
Yeah.
This makes it really hard to guarantee the accuracy of the knowledge graphs that we create. And we even saw evidence of this in RML conformance tests
Right.
that revealed these inconsistencies across different implementations.
Exactly. And without that formal grounding, it becomes so difficult to really study and compare these languages.
Yeah.
We can't answer these fundamental questions about their capabilities, like
Right.
what can one express that another one can't, or develop reliable optimization techniques to speed up the KG construction process.
Yeah, exactly.
So in this deep dive, we're tackling a fascinating new research paper, 2503.10385v2.pdf, that proposes a completely new approach. A language-agnostic algebraic foundation for building knowledge graphs.
A language-agnostic algebra.
Yeah.
Okay.
That sounds like it could be a huge turning point. Yeah. So our mission today is to dig into the core ideas behind this algebraic approach.
Okay.
And understand how it aims to address the current limitations in KG construction.
Okay.
We're going to get into the specifics of the algebra and what it could mean for the future.
Sounds good.
So to start, let's underscore why this push for formalization is so important.
Yeah.
As we've said, the informal nature of a lot of KG mapping languages, with RML being a prime example, 4, 5, 1, 6, 9, 20, 18, 8, 7, leads to some very real practical problems.
Yeah.
Different implementations of the same language behaving inconsistently, like this RML test showed 7.
Yeah.
Making it so difficult for systems to truly work together.
It's true.
It's almost like trying to build with Legos, where the instructions mean slightly different things depending on what box you bought.
Yeah.
And as you've said, without a clear formal definition, how can we be sure that the tools we're using are actually correct?
Right.
Or that the optimizations that we apply don't accidentally change the meaning of our mappings?
Right.
Plus, how do we compare different mapping languages in a meaningful way? Their strengths, their weaknesses, what they're best suited for, without a common framework.
Common rigorous framework, exactly.
Right.
And what's really exciting about this paper is that it doesn't try to formalize just a single language.
Okay.
It aims for a general formalization,
Okay.
a universal foundation that different mapping languages can be built on and analyzed with.
So what is the central idea behind this algebraic foundation? What does this language-agnostic algebra actually look like?
The core concept is to use a language-agnostic algebra to define the rules for transforming data from different sources, databases, CSV files, JSON documents, all of them into RDF-based knowledge graphs.
Okay.
And this algebra itself is based on a familiar concept,
Yeah.
the relational data model.
Okay.
But instead of just dealing with these simple data values, this model uses what they call mapping relations in the paper section 3.
Okay.
These relations can actually hold RDF terms, those fundamental building blocks of RDF,
Right.
like web addresses or IRIs,
Right.
blank identifiers, and literal values directly as content.
Okay, so we're moving beyond just tables of text and numbers.
Exactly.
How are these mapping relations structured?
One key element is the mapping tuple definition 1.
Okay.
You can think of it as a row in a database table,
Okay.
but it's more flexible.
Yeah.
Instead of having a fixed number of columns with single values, it's a partial function.
Okay.
It maps a specific set of attributes, the column names, to either RDF terms or a special error value, which is represented by the Greek letter epsilon.
Okay.
This is a clever way to handle situations where some data might be missing or couldn't be processed correctly.
Okay.
And the paper also defines when two mapping tuples are compatible. Essentially, they don't disagree on the value for any shared attribute.
Okay.
And how those compatible tuples can be merged together.
That makes sense. So if we have a collection of these mapping tuples,
Yeah.
all with the same set of attributes, that forms a mapping relation, right?
Exactly. A mapping relation definition 2 has a schema, which is that finite set of attributes.
Okay.
And an instance, which is the actual set of mapping tuples that adhere to that schema.
Okay.
So at its heart, it's a standard relational table.
Right.
But the individual cells can contain these richer RDF terms or the error value.
So how do we actually translate these mapping relations into an RDF data set that we can use and query?
That's where 4 special attributes come into play.
Okay.
As for the subject of an RDF triple, for the predicate, the relationship,
Okay.
AO for the object,
Okay.
and AG for the graph identifier definition 3.
Okay.
If a mapping relation schema includes these 4 specific attributes, then each tuple within that relation can potentially generate a single RDF triple.
Okay.
The values in the as, app, and AWA columns directly become the subject, predicate, and object of the triple.
Okay.
And the AG column specifies which named graph within the RDF dataset or the default graph if it's not specified the triple belongs to.
Right.
And the paper provides some examples,
Okay.
example 1 and example 2, that illustrate this process,
Okay.
showing how these special attributes, along with the sets IVAL and N, help define that final RDF dataset.
I see. I'm starting to get a clearer picture of how this relational style model can represent the fundamental components of a knowledge graph.
Right.
Now, you mentioned 5 types of algebraic operators.
Yes.
What are those operators, and how do they actually manipulate these mapping relations?
These 5 operator types, section 4, are the core of this mapping algebra.
Okay.
You combine them in different sequences to define these complex data transformation pipelines.
Okay.
The first type is the source operator.
Source operator, that sounds like the entry point.
Exactly.
Where we bring in the raw data into the system.
The source operator definition 6 is what's called a nullary operator.
Okay.
It doesn't take any input mapping relations.
Okay.
Its purpose is to create an initial mapping relation by establishing a relational view of that raw data source.
Okay.
Because this algebra aims to be universally applicable. It needs a way to handle all these different data formats and methods we use to query them.
Right.
So to do this, the paper introduces the concept of source types, definition 4.
Source types.
Yeah, think of it as a blueprint for interacting with a specific kind of data.
Can you give us a little more detail on that?
Sure. Imagine a source type as a contract
Okay.
that defines how to work with a certain type of data source, like a JSON file or a relational database.
Okay.
It specifies the types of data objects involved,
Okay.
the raw data, maybe some intermediate structures after parsing,
Okay.
and the final values we want to extract. It also specifies the query languages that can be used to pull that data out,
Right.
like XPath through XML or SQL for databases. The functions needed to execute those queries.
Okay.
It also includes this cast function, which converts the extracted data into RDF literals, those basic data values in RDF.
Gotcha.
And the paper offers these informal examples of source types for JSON example 3,
Okay.
suggesting JSON path as a potential query language.
Okay.
And for CSV files example 4,
Okay.
where the column headers might serve as these simple query expressions.
Okay.
So this provides this language-agnostic entry point for all this different data,
Okay.
abstracting away the specifics of those different formats.
So a source operator takes a specific instance of a data source,
Yeah.
say the particular JSON file,
Right.
and based on a query to select some initial data within that source
Uh-huh.
and a set of instructions,
Yeah.
mapping the desired attributes to further queries within that selected data,
Right.
it produces an initial mapping relation.
Exactly. The source operator definition 6 takes a specific data source S,
Okay.
a query Q, to select those initial context objects from the source,
Right.
and a partial function P
Okay.
that maps the desired attributes in our mapping relation to specific queries
Okay.
that will extract the corresponding values from those context objects.
Okay.
And then it applies the cast function
Uh-huh.
to turn them into RDF literals.
Right.
Examples 5 and 6 in the paper walk through a step-by-step scenario
Okay.
using a CSV file.
Okay.
to show exactly how a source operator would work in practice,
Okay.
creating a mapping relation with attributes like id, first name, and age,
Okay.
populated directly from the CSV data.
Okay, so that's how we get our initial data into this framework.
Right.
What's the next type of operator?
The second type is the extend operator definition 10.
Okay.
This is what's called a unary operator,
Okay.
meaning it operates on a single input mapping relation,
Okay.
and its purpose is to add a new attribute to that relation. The values for this new attribute in each tuple are calculated based on an extend expression.
Extend expressions, what can those involve?
Extend expressions, definition 8, are defined recursively,
Okay.
allowing for increasingly complex calculations. They can be simple, like a constant RDF term, or a reference to an existing attribute within that relation.
Okay.
But they can also involve what are called extension functions, definition 7.
Okay.
These are functions that take RDF terms and the error value as input
Okay.
and produce a new RDF term or error value.
Gotcha.
A concrete example the paper gives is a function called toint, example 7,
Okay.
that tries to convert an XSD.string literal, representing an integer, into an XSD.integer literal. Extend expressions can then apply these extension functions to other extend expressions or to existing attributes.
Gotcha.
And definition 9 details exactly how those expressions are evaluated for each mapping tuple. Example 8 shows how that toint function might be applied to an age attribute.
So an extend operator allows us to derive new information.
Yes.
Or transform existing information within our mapping relation.
Correct.
So for example, we could create a full name attribute by combining first and last name attributes.
That's out. You could use it to construct IRIs based on values and other attributes. Perform data type conversions. Concatenate values from multiple attributes using these extension functions.
Okay.
And example 9 demonstrates how the mapping relation that we created from that CSV file could be extended with a new attribute by applying the toint function to that existing age attribute, trying to convert those age values to integers.
That sounds super versatile.
Yeah.
What are the remaining 3 types of operators?
The final 3 types are basically the workhorses of relational algebra, adapted to work with mapping relations. Projection definition 11, equijoin definition 12, and union definition 13. Projection lets us select a specific subset of the attributes in a mapping relation. So we focus on the information we need. Equijoin enables us to combine 2 mapping relations based on equality conditions between certain attributes. Think of it as linking 2 tables based on matching values in certain columns. And union lets us merge 2 mapping relations that have the same schema. Combine their tuples into a single larger relation.
Gotcha.
And example 10 illustrates the projection operator.
Okay.
The formal definitions clearly outline how equijoin and union operate within this framework.
So with these 5 types of operators,
Right.
source to get the data in, extend to transform and add information,
Yeah.
project, equijoin, and union to manipulate and combine data.
Right.
We can construct complex expressions to map the data
Exactly.
from different sources
Yeah.
into a coherent RDF knowledge graph.
Exactly. And this leads to the second major contribution of this paper, demonstrating how this language-agnostic algebra can be used to provide a formal, unambiguous, meaning formal semantics for a widely used mapping language, RML Section 5.
Okay.
This shows how practical and powerful the algebra is,
Okay.
offering a rigorous definition where before there was informality.
So they're not just proposing a theoretical system.
Right.
They're showing how this actually connects to the real world of knowledge graph construction.
Exactly.
How do they do that?
They present an algorithm 1 that takes an RML mapping, which is typically represented as an RDF graph, and translates it systematically into an equivalent expression using the operators in the algebra.
Gotcha.
This algorithm provides a formal definition of what each component of an RML mapping means in terms of these algebraic operations. And they emphasize that this formal semantics aligns with the existing informal specifications of RML version 1.1.25. And they even validated this by running the official RML test cases 8 on a prototype of their translation process.
Wow, that validation is compelling.
Yeah.
What are the main steps involved in translating from RML into the algebra?
The algorithm starts with a normalization phase.
Okay.
Because RML offers some flexibility in how those mappings are described.
Right.
This phase aims to convert any RML mapping into a standardized uniform structure.
Okay.
There are 6 steps, which are detailed in Appendix A.
Okay.
These include things like fully expanding definitions of class IRIs,
Okay.
handling shorthand notation for constant values and term maps,
Okay.
splitting up predicate object maps that have multiple entries,
Okay.
dealing with referencing object maps, and triple subject maps that involve multiple graph maps.
Okay.
And the purpose here is to simplify that RML structure to make the translation into the algebra more direct and consistent.
So putting every RML mapping into a common well-defined format before the translation?
Exactly.
Okay.
After normalization, the algorithm enters the main loop, where it processes each triples map defined in that normalized RML mapping for each triples map. It constructs a corresponding part of the algebraic expression.
Gotcha.
And the first step is to create a source operator based on the logical source defined in that RML. A function called second root query definition 14 is used to extract the necessary information about the data source and the initial query to access it. And example 11 shows that. Then another function, extract queries algorithm 2, pulls out the relevant query expressions from the term maps associated with that particular triples map. Example 12 illustrates that.
Okay, so we've now got our source data represented as a mapping relation in the algebra.
Right.
How do we define the actual RDF triples that we want to generate?
This is where the extend operator is critical for the subject map and the predicate map of the RML triples map. The algorithm adds these extend operators lines 9, 10 of algorithm 1. The extend expressions for these operators are generated using the createXTextBar function algorithm 3. This function takes into account whether the RML term map specifies a constant RDF value, a reference to a value within the data source, or a template for constructing the RDF term.
Gotcha.
Like using values from different columns to build a URL. The createXTextBar function uses several of those extension functions we discussed, defined in Appendix B, such as to IRI for creating IRIs, to B nodes S2B for creating blank nodes, to literal for creating literal values, and concat for combining strings. And sample 13 shows an example of that.
And what about the object map?
Yeah.
The O in our subject predicate object triples.
The object map, lines 1122 of algorithm 1, is a bit more involved. We need to consider both standard object maps and referencing object maps. In RML, a referencing object map defines a link to the subject map of another triples map. So the algorithm recursively processes that linked triples map, creating its own algebraic representation. And then performs an equijoin operation line 18 based on any join conditions. Specified in the RML mapping. Ordinary object maps, which directly specify the object term, are handled similar to the subject and predicate maps using extend operators.
And finally, we have the graph map, which determines if a triple belongs to a named graph or to the default graph.
The algorithm checks if the triples map in the RML includes a graph map. If it does, it adds an extend operator to set the ag attribute based on the IRI specified in the graph map lines 23, 24. If there's no graph map defined, it adds an extend operator that sets the ag attribute to the default graph IRI, which is typically represented as rr.defaultGraph line 26.
Gotcha. So after all the components of a single RML triples map have been translated into the algebra, the mapping relation, which now includes the as, app, AO, and ag attributes, is projected to keep only those 4 attributes. Then these resulting mapping relations from each triples map are combined using the union operator line 27. And the output of the whole algorithm is a single mapping relation that represents the complete RDF dataset defined by the original RML mapping line 28. This formalization of RML is great. It shows how practical and powerful the algebra is. So this translation process doesn't just prove that the algebra is powerful enough to capture the meaning of RML, but it also provides a formal, unambiguous definition of RML itself. It's a huge step forward.
It is.
But the advantages of having this foundation extend beyond just providing a formal semantics for RML. The paper also looks into how the algebra can be used as a basis for optimization. Within Knowledge Graph Construction Tools, Section 6. optimization, that's something everyone in data processing is interested in.
It's true.
How can this algebra help make that KG construction process more efficient?
Because we now have a formal representation of the entire mapping process as an expression composed of these operators.
Right.
We can explore algebraic equivalences.
Okay.
These are rules that allow us to rewrite a given mapping plan, that sequence of algebraic operations, into a different but mathematically equivalent form, with the goal of finding a form that is more efficient to execute.
Gotcha.
And the paper presents several important algebraic equivalences.
Can you give us some specific examples of these optimization techniques?
Sure. One key set of equivalences focuses on projection pushing section 6.1.
Okay.
The idea here is to reduce the size of the intermediate mapping relations as early as possible in the pipeline by removing attributes that aren't needed for later operations. Proposition 1 in the paper shows the conditions under which a project operator can be moved before an extend operator. Proposition 2 shows how you can introduce an additional projection step, which then creates more opportunities for pushing projections earlier.
Gotcha.
And corollary 1 combines these two for even greater flexibility. In optimizing the projection placement. Propositions 3 and 4 highlight specific cases where project operators can be completely removed if all the necessary attributes are already present.
So less intermediate data should directly translate to faster processing and reduced memory usage.
Exactly.
What other kinds of optimizations does the paper discuss?
Another important set of equivalences deals with pushing or pulling extend operators. Relative to equijoin operators. Section 6.2. Proposition 5 outlines the specific conditions under which an extend operator can be moved, either before or after an equijoin. This is important because the optimal ordering often depends on the selectivity of the join operation. How much it reduces the number of tuples. If a join filters out a lot of tuples, it might be more efficient to do the join first and then apply the extension only to the smaller set of tuples. But if the join creates a much larger number of tuples, it could be better to do the extension beforehand. Finally, Proposition 6 shows that under certain conditions, you can swap the order of two consecutive extend operators. This might seem simple, but it can be helpful for grouping extensions together. Or for positioning them in a way that makes it easier to push or pull them around join operators.
So these algebraic equivalences give us a formal and rigorous way to think about and implement optimizations in KG construction. Optimizations that might have been more ad hoc in the past. This all sounds incredibly promising.
It is.
What are the main takeaways from our deep dive into this algebraic foundation for knowledge graph construction?
I think the core takeaway is the introduction of a formal language-agnostic algebra for describing the process of building knowledge graphs from diverse data sources. This provides a much-needed, solid theoretical underpinning for a field that has seen a lot of adoption but has lacked this kind of rigorous foundation. The paper also demonstrates how this algebra can be used to formally define the semantics of an existing language like RML. And by presenting a set of algebraic equivalences that can serve as a basis for sophisticated query optimization techniques.
And what are the potential broader benefits for the future of knowledge graph construction?
Well, this work paves the way for better KG construction tools. With a formal algebraic framework, we could be more confident in the correctness of our implementations and in the effectiveness of our optimization strategies. It also allows for a more rigorous comparison of different mapping languages, which could lead to better language design in the future. The language-agnostic nature of the algebra opens up some exciting possibilities for KG engines that can understand mappings in multiple languages.
The paper also mentions some avenues for future research, right?
They do. They outline several promising directions for future work, Section 7, including extending their algebra to formally define the semantics of other mapping languages, enriching the algebra itself by introducing new operators, discovering new algebraic equivalences, and developing concrete algorithms and implementations for those optimization techniques. The fact that the algebra is language agnostic also points to the development of multilingual KG processing engines in the future.
So this research isn't just about formalizing the present.
No.
It's about laying the groundwork for the future of how we build and manage knowledge.
This is a fundamental step towards a more rigorous and efficient approach to knowledge graph construction,
Okay.
which is becoming more and more critical in our data-driven world.
This has been a fascinating deep dive.
It has.
It really underscores how foundational research can have these profound and practical implications.
It really does.
For those who want to explore the technical details further,
Yeah,
we recommend checking out the research paper on ArcBSEF.
absolutely.
The link is https://arcscef.org/2503.10385.
And maybe this deep dive will leave you thinking, how might a more formal understanding of data integration and knowledge graph construction affect your own work or areas of interest?
Yeah.
What are the challenges in building these interoperable knowledge systems?
Right.
And how could a well-defined formal foundation help us overcome those challenges?
There's a lot to think about.
It is.